Variances are going to have units of squared blood pressure, squared millimeters of mercury. Maybe it'd be best to go back to the original units, and the best way to do that would be to get into the squares. And what a standard deviation does is just take the square root of the variance. So going back to the slide 2 slides ago, the standard deviation 27 is nothing more than the square root of 773. And finally, the other way that sometimes people describe variation is they say, let's go back to the rankings. Okay. And then I said, when you line people up, the person in the middle of the line had a blood pressure of 142. The person who's the 75th percentile in that line has 25% of the people in front of him, 75% of the people behind him. His blood pressure was 160. The person who's the 25th percentile has 25% of the people behind her, 75% above her. So in between the 75th and the 25th percentile, we have the middle half of the people. Because there are 25% of the people above the 75th percentile, 25% below the 25th percentile, meaning there are 50% of the people in between the 25th and the 75th percentile. The distance between their blood pressures, the distance between the 130, which was the blood pressure for the 25th percentile, and the 160, which was the blood pressure for the 75th percentile, is a distance of 30 blood pressure units, 30 millimeters of mercury. And that says that the middle half of the distribution of these blood pressures are separated by a gap of 30 millimeters of mercury. So I mean, any two people in that middle half of the distribution can have blood pressures no different than 30 millimeters of mercury. So now going back to this one graph I didn't describe to you, this box and box plot over here. This box here describes the location of the middle half of that distribution. The bottom of the box is where the 25th percentile of the person's blood pressure was, at 130. The top of the box is where the 75th percentile's blood pressure was, at 160. So the box stretches or lays over that range of 130 to 160. The dotted line inside the box is where the median blood pressure was. That was 142, I believe it was. This little cross, which happens to be right around that same dotted line, actually it's a little bit above the line, is where the mean was. That's the 147. So the box is describing the middle half of the distribution of blood pressures. What goes above the box and what goes below the box are what we call whiskers. They describe the outliers, the people who were above the 75th percentile and the 25% below the 25th percentile. And what SAS does is first use a dash to plot or they're below 25th percentile, but they're still within 1.5 interquartile range units of that central box. And you remember the interquartile range was 30 units. Any blood pressure person above the 75th percentile, whose blood pressure is between 1.5 times 30, 45 units, will be represented by a dash. People above that will be represented by zeros until they reach another 1.5 interquartile ranges above the top of the box, then by stars after that. So the different symbols say how much away you are from the 75th percentile or below the 25th percentile. And you see, again, as we saw in the histogram, these little stars, these asterisks, that's the right plural for asterisk, tell you how the 75th percentile in terms of distance, in terms of interquartile range units. So these are various ways you can describe a continuous variable like a blood pressure, in terms of its averages and in terms of its variation. And this tends to be what you see back in those tables that we saw for table 1. People would either display perhaps the average blood pressure along with the standard deviation, or they would prefer to report a median blood pressure with an interquartile range. Let's see what they did. Let's go back to those 2 tables that we looked at, those 2 studies. computer said it's slow today, so you have to put up with me. Here's table 1 coming up from the big randomized trial. So here's age. What they reported were means and standard deviations. For weight, means and standard deviations. All these numbers here are for a continuous variable are being described by an average and a standard deviation. If you had outliers that you wanted to not affect your average in terms of a mean, you might display a median. If you do that, you might display an interquartile range next to it. So that's typically how we describe data, say in table 1. And that's hopefully everything that people had seen before. And before I forget, let me make a plug for those papers that were sent around. They're very good descriptions of basic biostatistics. So if you have a few minutes, and if you haven't had much training in biostatistics, read those papers. I think it will help you understand a lot better the type of analysis that people do for data that we're going to be looking at. But let me spend the rest of today talking about the issue of statistical inference. Statistical inference means making statements beyond your data set. You can do a data set like they did in the 2 studies we looked at. Up with a risk ratio, an odds ratio, perfectly describe what's going on in that data set. But you don't do studies just to describe the effect of a risk factor in one group of people. You want to talk about the likelihood that a risk factor will affect other people in terms of developing that outcome. So what you'd like to do is generalize results to bigger populations, go beyond your data set, and describe not only what's happening in these data, but describe what's happening in the type of people who are in this particular study. And that's what statistical inference means, making generalizable statements, talking about going beyond what's in a particular single data set. And there are 2 ways we do that. The most common is something called tests of statistical significance. We do significance tests. What a significance test is, it's measuring the consistency of what you have in the data with a particular study or with a particular statement. If we go back to that previous large randomized trial, they wanted to know whether a lifestyle intervention or a particular drug, metformin, would decrease your risk of developing diabetes. So what a test of significance in such a study would be saying is how consistent are the data you observe with the statement that this drug doesn't affect your risk of developing diabetes, or this lifestyle intervention does not affect your risk of developing diabetes. So all tests of significance are addressing what is known as the null hypothesis, a statement that says your risk factor has no effect on your outcome. Regardless whether you take this intervention or not take this intervention, you have the same chances of developing an outcome. It doesn't affect your risk of developing an outcome. So in the previous study, the null hypothesis would be that people given placebos and people given metformin and people giving a lifestyle intervention all have the same risk of developing the outcome, namely risk of developing diabetes. In other words, the risk factors, the interventions have no effect on that outcome. Now that's probably not the reason you did the study. We usually do studies hoping to show that a risk factor prevents an outcome or a risk factor causes an outcome. But when you do tests of significance, realize all you're asking is how consistent are your data with a single statement, the null hypothesis. The key question you're asking yourself is, do the data support the null hypothesis? They tell you nothing about whether the data supports alternative hypotheses. All the focus is on one statement that the risk factor has no effect on your outcome. Now, there are lots of different tests of significance for doing significance testing, lots of different ways to get p-values. We'll talk about a few of them today. What determines what type of test you use is the outcome scale. Remember, we talked in the very beginning about different types of outcomes, nominal outcomes, continuous outcomes, ordinal outcomes. The type of outcome determines what type of test of significance you're doing. I'll try to show that as we go along with a few examples. But there's another way to make statements about statistical inference besides doing tests of significance. It's by constructing confidence intervals. Confidence intervals give you a range of values which are supported by your data. Not only do you give the reader one odds ratio, for one risk